Okay, so let's compute limits at infinity through examples. So let us consider the function f of x equals 1 over x. And let us observe the behavior of the values of f as the values of x gets bigger and bigger. So if we look at the table, as we let the values of x approach infinity, the values of our y, or the values of 1 over x, get smaller and smaller. So we can say that the values of 1 over x approaches 0. So in limitation, we have the limit of 1 over x as x approaches positive infinity is equal to 0. On the other hand, we say also that the limit of 1 over x as x approaches negative infinity is equal to 0. Okay. Let's show this using a table of values again. So as we decrease the values of x, or meaning as we move x farther and farther away from 0 negatively to the left of 0, we see that the values of 1 over x get smaller and smaller negatively, okay? They maintain their negativity since x is negative. 1 over x is always negative, but if you look at the values, they move closer and closer to 0. Hence, the limit of 1 over x as x approaches negative infinity is 0. So this is a pretty trivial example because you will use this theorems, or you say formula, in evaluating limits at infinity. This is very trivial. Now, observe that when you raise 0 to a real number n, or to a real integer, to an integer n, 0 raised to n is always 0. And by properties of exponents, 1 over x raised to n can be written as 1 over x, and then the whole fraction is raised to n. So therefore, if we evaluate the limit of 1 over x raised to n, we can apply the power law of limits. So we have the limit of 1 over x raised to n as x approaches positive or negative infinity is 0. Remember, the limit of 1 over x, so if you have the limit of 1 over x as x approaches infinity or negative infinity is 0. And by the power law, if you have 1 over x raised to n, you can just take the limit of 1 over x, and then everything is being raised to n. So when you raise everything to n, the limit of 1 over x as x approaches positive or negative infinity is equal to 0. So 0 raised to n is 0. So therefore, the limit of 1 over x as x approaches positive or negative infinity is 0. So let's take an example. Let's have the limit as x approaches infinity of 1 minus 3 over x cubed. Now here we have a difference of two functions. So we will use the difference law to distribute the limit. So we'll have the limit of 1 as x approaches infinity minus 3 times the limit of 1 over x cubed as x approaches infinity. Now, remember, when we distribute the limit to each of these here, this is just 1 over x cubed with a multiplier of 3. So 3 is a constant multiple. So using the constant multiple law, we can factor 3 out of the limit. That's why we have this. Now remember that when we are evaluating infinity or limits at infinity, we aim to simplify the problem. We aim to get something like this. The limit as x approaches positive or negative infinity of 1 over x raised to n is 0. This was the trivial example that we've shown earlier, and this is your guide. This is your goal when you're evaluating the limit as x approaches positive or negative infinity. So for this case, we are able to transform one of our given into this. This is a case where n is equal to 3. And we know that the limit of 1 over x cubed as x approaches positive infinity is 0. So we have 1, which is the limit of 1 as x approaches positive infinity, minus 3 times 0, which is the limit of this. So we have 1 minus 0 is equal to 1. So therefore, we have the limit as x approaches positive infinity of 1 minus x cubed is indeed equal to 1. So let's take a more complicated example. Suppose we have the limit of 5x minus 2 over x minus 3 as x approaches negative infinity. Okay, remember we aim to simplify the function for us to come up with something like the limit of 1 over x raised to n as x approaches positive or negative infinity. But it is not easy to do that here, but it is possible. So the first thing that we need to do is we determine the highest power of x in the denominator. Okay? Remember the exponent of x is 1. The x is just x raised to 1. And for 3, this is just 3 times x raised to 0. So therefore, the highest power of x in the denominator is x. And then we divide the numerator and denominator by x. There's nothing wrong with this because when you divide the numerator and denominator by the same number, it's just the same as dividing or multiplying the function by 1. Okay? So it's x over x. So when we do that, we get something of this form. We divided the numerator and denominator by x. And then we can cancel this x out, giving us 5. And then this one will get 2 over x. You can also cancel this out, so we get 1, and we have 3 over x. And then we will apply the different algebraic limit laws. So this is the same as example 1. When we evaluate this and this. But the first thing that we need to do is we distribute the limit, like the quotient law. We distribute the limit to the numerator and denominator. And then we apply what we did to example 1. So we have the limit of 5 minus 2 times the limit of 1 over x. In the denominator, we have the limit of 1 minus 3 times the limit of 1 over x. Now we know from the illustration that this is a trivial case. The limit of 1 over x as x approaches negative infinity is 0. The limit of 5 is 5 since 5 is a constant. The limit of 1 as x approaches negative infinity is 1 since 1 is a constant. So we have 5 minus 2 times 0 over 1 minus 3 times 0. Or 5 minus 0 over 1 minus 0, which is just equal to 5. So therefore, the limit of 5 over x, the limit of 5x minus 2 over x minus 3 as x approaches negative infinity is equal to 5. So let's have another example. An example that involves exponents that are greater than 1. This may look complicated to you, but we just apply what we did, the same thing with what we did to example 2, and you'll get through it. So please follow through the solution. So again, you determine the highest power of x in the denominator. In this case, we have x cubed. And you divide the numerator and denominator by x cubed. So you'll have this. Divide by x cubed. And then after that, we try to simplify the numerator and denominator separately, giving us this. X squared over x cubed we were left with x in the denominator. X over x squared, we have x squared. X over x cubed, we have x squared. X cubed over x cubed, we have 1, so we're left with 6. 5x over x cubed, or x over x cubed, we're left with x squared. 3 over x cubed, we're left with 3 over x squared. Now, if you look at the terms, if you look at each of the terms, the trivial case or the illustration, the one that I've told you earlier, I've been telling you earlier, is applicable to each of these. So, by applying the limit laws, you just distribute the limit. So this is what we had in the previous slide, and then we apply the algebraic limit laws. So you just distribute the limits, and then, so now this is pretty obvious. You get the limit as x approaches negative infinity of 1 over x raised to n, which is just 0. So this gives us 3 times 0 minus 5 times 0. Limit of 6 is 6 plus 5 times this is 0 minus 3 times the limit of this is 0. So we get 3 times 0 minus 5 times 0. So the numerator is 0, this is 0, this is 0. So we get 0 over 6, which is 0. So the limit of 3x squared minus 5x over 6x cubed plus 5x minus 3 as x approaches negative infinity is indeed 0. Now here is another example, and we will just use the techniques or the steps that we've used previously. So suppose we have the limit as x approaches positive infinity of 5x to the 5th plus 3x minus 1 over 6x cubed plus 5x squared plus x. Again, we determine the highest power of x in the denominator. This time it's x cubed, and we divide the numerator and denominator by x cubed. This gives us this form, which when simplified gives us 5x cubed over x, 5x to the 5th over x cubed is 5x squared. So you just simplify, and then we apply the algebraic limit laws, meaning we distribute the limit to every term. So here, and we also apply the constant multiple law if applicable. So for example, in this case, 5 is a multiplier, so that's why we took 5 out. Okay, so if you look at this, the limit of this, we know that the limit of this is 0, the limit of this is 0, the value of this, the limit of this is 0, the value of this limit is 0. This is a constant, so the limit of 6 is just 6. Now, this is x squared, which we can use or apply the power law. Remember, the limit of x as x approaches positive infinity is positive infinity. Applying the power law, you raised it to 2 or you square it. So positive infinity squared is just positive infinity. That's why we have positive infinity plus 3 times 0 minus 0 plus 6 plus 5 times 0 minus 0 is just, look at this. This is 0 to infinity plus 0 is infinity. This is 0, so 6. So we have infinity over 6, or we have positive infinity. So we have the limit of this as x approaches infinity is just positive infinity. So this time we learned the steps to evaluate the limit of a rational function at positive or negative infinity. So the first step is to determine the highest power of x in the denominator, and then you divide the numerator and denominator by the power of x that you identified in step 1. And then you apply the laws on limits or the algebraic laws on limits. So usually it would be the sum and difference law, wherein you distribute the first thing that you need to do is you apply the quotient law, wherein you distribute the limits, the numerator and denominator, and then you apply the sum and difference law, where you distribute the limit to every term in the separately in the numerator and denominator, and then you apply the constant multiple law, where you factor out the constant multiplier from the limit, and then you apply the trivial example that we presented, that is the limit of 1 over x raised to n as x approaches positive or negative infinity is equal to 0. So that's just it. But take note that the limit of 1 over x raised to n as x approaches positive or negative infinity is 0. And if you have a multiplier, let's say c, a constant, you just take it out. So it's just equal to 0. So before we end, let me leave you with some very important notes. This is the property that tells you what happens when you multiply positive or negative infinity by a constant, or when you divide positive or negative infinity by a constant.